I wanted to go through this, the wiki page on the spinodal. I think it seems like it's pretty good. This part's good. This part's coherent. Oh, sorry. Yeah. About that. Like the PowerPoint on spinodal just kind of gives the equations and doesn't exactly say where they came from. Like actually almost everything you see, like this paper does the same thing. Actually, this paper doesn't even give the equations. Yeah. He just kind of mentions in passing a little bit about it. And the part, and then I cited that Hashimoto, and I thought that that was a pretty good description, but actually when you get down to it, let's see, phase stability. So the first things like this Hashimoto thing, which that was what I kind of learned it from this paper. So, but when you go to do it, like he just gives this equation. The wiki page does a better job. He just gives that equation, and then he just kind of gives, let's see, does he give the rate equation? Yeah, he gives the rate. So there's two equations. This is the free energy equation, and then this is the rate equation. And they're loosely related to each other. And he's just giving them, like he doesn't say like what this is, you know. So the wiki page kind of says what that is. Then the wiki page just dumps this equation on you. And if you go look, there's also there's a guy who derives the kinetics equation for spinodal that I found, this spinodal kinetics, I think in Utah or something. But so he derives that kinetics equation, but it turns out like it's not, you can't really follow this very easily, you know, like it's a lot of differential equations. The problem is it's like 3D, you know, so it isn't a 1D problem. So you have to use tensors. That starts out, that's the beginning of the problems. It's like mostly people don't want to deal with tensors. This you kind of have to because it's in 3D space. You're trying to develop this 3D structure. And then the other big problem with it is that, so I don't know if I've emphasized it much, but basically people emphasize that there's a distinction between kinetics and thermodynamics, like, and you can't mix the two, right? So the issue with spinodal is that you have to mix the two to get the answer, because it's basically determined by the balance between transport and this thermal driving force, and that leads to this phase size that you end up with. Right, so you kind of have to cross a couple lines. And Kahn, I guess most of the stuff cites this Kahn paper, and then that stuff is indecipherable too. So you end up with these two equations, though, in the end, right? That like this this equation and the kinetics equation. From this equation, you can get what the critical size is for the spinodal decomposition. Or for sizes smaller than that, it doesn't decompose, and for sizes larger than that, it does. If this thing is negative, if this second derivative of the free energy is negative. So this is like the curvature of the free energy curve. So remember I said, like, if it's a frown curve, it face up rates. If a smiley curve, it's a positive is a smiley curve and frown is a negative of this thing, and 0 is a critical point. So if you set that thing to 0, or if you set this to 0 and then solve this thing, then you can calculate what this critical size is. You see it's a square root of a negative. So this thing has to be negative, meaning it's a frown, means a phase separating. So you're into the spinodal region to get this critical size. And if you have size larger than that, it phase separates. If it's smaller than that, it dissolves. That's kind of the point of this first part. But the main thing of the spinodal is you're going to get a fixed size. So you have a size that's a happy size where it decides to grow for given transport properties and a given thermodynamic driving force. This doesn't give that to you. To get that, you have to go to this, you have to have the diffusion equation, but they write the diffusion equation. It's a fixed second law is normally like dc dt is the diffusion coefficient times the second derivative, and usually you write it in 1d, like d squared, second derivative of c dx squared, or it could be xyz, right? If you wanted to do it, this tensor, this del means d dx dy dz, but this thing, if it's just del, that gives you a vector. In other words, it's going to be, so that's why I get this thing turned on here. But so anyway, then it gets into like math. So you gotta kind of slides for this. But basically, let's see, is that going to show up? Why is it? Oh, it's a reverse projection thing. Oh, yeah, that helps. Invisible auto tune. Everything seems to be happy, except it's not showing the focus. There, that's happy now. All right. So this is called the del operator. That like del C is dx, dc, dx, dc, dy, dc, dz.
So I think the light's so great. Yeah.
All right, it's pretty weird. All right, just kill the light. Oh, that's the background light. Is that all right? That's good. That's weird. Usually it works with the light, I think. Anyway, times these unit vectors. So this is a vector.
Okay, got worse again.
Oh, it's focusing now. What did I do wrong here? Is that going to help? All right, we'll see. Anyway, this EY, EZ, right? So these are unit vectors for the XYZ. So this thing's a vector. So you take this, takes a scalar concentration and turns it into a vector. And you know that the free energy is a scalar, like it doesn't have direction. The volumetric thing. So, or little f is a volumetric thing. So anyway, so the only thing you could possibly use is that thing squared, or that thing to the fourth power, or whatever, which is the same thing as the Langevin, right? We gave that Langevin free energy to get the whatever decomposition thing, and it did an order parameter, and it was like even powers of order parameter. So it's kind of like, so Kahn came along much later than Langevin, and he's using Langevin's idea to say, like, he's going to use this del C squared thing to talk about this. And then in the dynamics part, I might as well mention while we're here that there's also this del dot operator. So if the argument in here is a vector, then you have to either do del dot or del cross, which have names too. I don't remember the names of those, but that thing will be, so you have your vector thing, like whatever capital F would be a vector. F's not a good symbol. So you have your vector like B, and then like so what del will be like Vx dot, or let's see, Ex dot Vx, which this thing makes a cosine of the angle between the two vectors, and then it's the absolute, like not just the magnitude of the Vx and the magnitude of Ex, which is 1. Right. So it's just the angle between the two, and then d dx. So this basically ends up being dvx dx plus dvy dy, and these are vectors, and then this thing ends up being a scalar. That thing gives you a scalar. So, and then the cross product would be a sine instead of a, that's like the right hand rule thing. You get a sine instead of a cosine. This thing we aren't dealing with here, so we need to talk about that. This thing and that thing are the two things that we have. So, and for the first part is just that thing. Right? So anyway, so that's that business. Anyway, so he does this thing where he writes. I mean, if you follow that Wikipedia thing, it's just like one paragraph. It took me like 8 pages to do that. One paragraph, you know, but so you have the like the, let's say you have the Helmholtz free energy, or you have the Fourier-Huggins free energy. So somehow you're gonna have a free energy. In that wiki page you call it FB, and then FB depends on C. So you have it some average concentration. This is C naught is the average concentration, and then you take that. That's the going to be the free energy per volume, and you're going to integrate that over the volume, d volume. Then you're going to add to that this idea that you have a gradient. So you have, there's going to be, so in spinodal you're going to have this like uphill growth, right? So there's going to be this kind of gradient term that's adding to the free energy. In nucleation growth, you have a nucleus, and then it depletes the concentration near the nucleus, and that drives transport towards the nucleus so it can grow the crystal, right? That's the idea of nucleation growth. In spinodal, it just spontaneously happens. So here you don't have this kind of gradient term, but here this adds to the free energy of the system. So you have some kind of gradient term that's going to be dependent on this kind of del of the concentrations. It's going to be like dc dx, right? But since that ends up giving you a vector, you have to square it. And also for one reason, you have to square it because you're going to get total free energy over here. Total free energy is going to be integral of this volumetric free energy. This is the actual free energy for the sample that you have. And this is a volumetric per volume. And there's this kappa for the surface for the gradient, and the gradient is going to be judged by this thing, but you can't have that because that's a vector, so you have to square it. So you have to square that guy, and then dv. So that's that first equation. And so this equation also looks just like the Langevin, where the order parameter is dc dx for this situation, because of the thing that's causing the phase separation is this gradient thing. All right, so that's kind of that's the logic behind that equation, right? And then the way to so that's nice. You can have that, and that's like a picture of what's going on. And then you add in that you're going to have fluctuations. Like there's going to be some kind of noise pattern and the concentration, like temperature. We saw the picture of fluctuations, you know, so that kind of thing, which can be deconvoluted into sine waves. So you can have different sine waves, each of which has an amplitude, which in the wiki page they call small a, and then it's also going to have a wavelength. So you're going to have a wavelength, which in wiki page they call lambda, or a lot of people call it lambda. And then usually you're talking about the wave vector, or inverse space, which is going to be 2 pi over the wavelength of that wave. So that can be called k, can be called s, and it can be called q. Here in the wiki page you call it q, and q's a vector. Q's got a direction to it. So you have a concentration fluctuation in a certain direction. It's a wave, and it's going in it's a wave is moving in a direction, so it's a vector, right? And then you have space, like the space that you're sitting in, which is also a vector, which could be x, y, z, or it could be like r, if you want to have just one number, right? So if you have sine, if you're going to have a sine wave, the way to talk about its position in space is to say the wave vector dotted with this r vector. So you do like r dot q sine of that, and then a is an amplitude. Just something like that for the sine wave. So that's just describing they have a fluctuation in space, and then the dot product, again, that's going to be cosine of the angle between the two things times the values of the two, the magnitudes of the two. So it's just a way to talk. It's basically the projection, like we do cosine of the angle, we end up with a projection of one on the other. It's like the projection of the two vectors on each other, like what part of Q of this concentration fluctuation is in the direction R. That's like the idea. That's what the cosine takes care of. And then, so that's kind of how that works. And the magnitude of the fluctuation is at A. So then he does this, he just does a Taylor series expansion of this F of B thing. So he says F of B at concentration is a Taylor series expansion. F of B is C0. So F of B of C is F of B of C0, the average composition, and then plus the kind of the change in composition, which is, all right, so I'll just call it delta C. He calls it C minus C0. dF dC. So the derivative, this is Taylor series expansion. You do a derivative and you multiply it by the delta. And then for the second derivative, you do half delta squared, delta C squared. And then, so delta is different than del. Del's upside down delta. And deltas means the difference between the two. And this is done at C equals C0. But these derivatives are all at the average composition. And then if you plug in this sine wave for that, and the delta C becomes A, and somehow in this thing disappears. I'm not sure why, but that disappears. I guess with the fluctuation, the average one goes out or something. Anyway, if you plug this in, then you're going to end up with FBC0. So the derivative of sine is cosine. So you end up with cosine of the so here you'll end up with cosine of this R dot Q times A. A is the delta C and cosine's the dot product, and then plus A by 2, and then the second derivative. So this will end up giving you, let's see, how did I do this? A sine. So if this is just plugging it in, you get A sine 1/2 A squared sine squared. Well, this is just plugging in. Sorry, this isn't the derivatives. This is just plugging in for delta C. Delta C is this thing. So it's going to be like plus A sine of RQ, and then plus 1/2 delta C squared is A squared sine squared RQ, R dot Q, and then times the D squared F DC squared. And then he adds in the because it's FB plus this kappa, plus the kappa thing. So you add in the kappa thing, which is del C squared, which is going to give you A squared Q squared cos squared Q dot R, because the derivative of sine is cosine. The del of C is cosine and is squared. So it's cos squared C times kappa of Q dot R. Right. So you have a sine squared, and then you got this thing you have to integrate over volume. Integral of sine over volume, because sine, so if you take here to here, if you integrate that, that kills that, because sine goes plus minus, the integral is 0. But if you do sine squared, the integral is 1/2. And if you do cosine squared, the integral is also 1/2. So this thing goes to 1/2, and this thing goes to 1/2. Then you end up with 1/4 and 1/2 of that. So you'll end up with this equation. You'll end up, if you, this term goes away somehow. I don't know how that goes away, but basically it goes away. Then you end up with, after you integrated it, they have dF per volume equals A squared by 4 times del F over
Can you
DC.
keep the paper?
Sorry, yeah, that thing C equals C0 plus 2 kappa Q squared. So you'll just end up with that from this equation because you have A squared, Q squared, that ends up being Q squared, you have A squared here. This thing is like 1/4. 2 over 1/4 gives you the 1/2, and that was the derivative of the cosine. Somehow that gives you the 1/2. Anyway, it works out to be this equation for the free energy for the system. And then if you say the free energy goes to 0 at the critical point, so when you're at this critical Q value or critical like position, so 1 over lambda 2 pi over lambda c, so some kind of the system, like so you have your system and it goes into this region where this thing's negative, then you're going to get you end up with a size scale. So you say this thing at that point, at that critical point, that equals 0. For sizes larger than that, it's going to separate. Sizes smaller, it won't. So you set that to 0 and you solve for Q. That would be QC at that. Once you say 0, that becomes QC. You solve for QC and you get the answer, which is like, that gives you the first kind of step of, so the size scale that you're talking about is going to be 2 pi over the QC, which is going to be the square root of negative 8 pi kappa over d squared f dc squared when c equals the average composition. And then this thing has to be negative because you can't get a square root unless it's negative. That means that this is a frown. In other words, if you plot the free energy versus composition, it's a frown. That means the phase separates. That means you're in the spinodal region. All right, so that's the simple part, believe it or not. That part is like possible to understand. You don't need to understand this, but basically that part could be understood. The rest of it, so, and that just tells you that its size is larger than some size scale. You're going to get phase separation for the spinodal, and its size is smaller, it won't separate. So you have like a cutoff size, and bigger things will separate, smaller things won't. And it follows this kind of basically the Langevin idea, and it couples like having an interfacial thing with the bulk energy of the system, like couples the two together. But it doesn't have any transport issue. So it doesn't have any possibility of deciding like what this phase size is going to be. I think maybe they realized the main signature is going to be that it sets up this size scale, right? And so how do you get that size scale? That's like the main bread and butter thing of it. So anyway, like I said, I don't exactly understand how to get the other part of it, but I can give you some hints about where he's going, at least on the wiki page. And then it doesn't, see, the wiki page is kind of okay for that part I just did. I mean, you can figure it out from there, but this other, the other part's more difficult. So you have like Fick's second law, right? So you have, which is like dc dt is going to be the diffusion coefficient times del squared c. So del squared c is a scalar. It's going to be the second derivative of c dx plus the second derivative of c dy plus the second derivative of c dz squared. All right, so this thing is like that thing, it's a scalar. So the first del is a vector, the second del is a scalar, because it ends up being, if you do another del on a del, you end up with like ex dot ex, and the theta 0 is 0 and it's cos of theta, so that's just 1 and the vector disappears. That's kind of how it works. So even though the first one's a vector, del of something, a scalar is a vector, but del squared is a scalar. And then you end up with this dc dt thing. So anyway, so that's the thing we usually have. In other words, that would be just dc dx squared, d squared c dx squared if it was in one dimension. Right. So anyway, but the way they write this thing here is like dc dt equals m del squared mu. Mu is the chemical potential, like dg dn. dni or whatever. Right, so that'll be ui. Right. So anyway, what does chemical potential have to do with concentration? Well, we have like chemical potential is like KT times ln of concentration, more or less, right? In other words, it's usually delta mu, and this is usually the activity, not the concentration. But basically, there is a relationship between the chemical potential and the concentration. And if you're talking about small fluctuations, so the only way to get this equation is to say you have small fluctuations. In that case, like E of x is 1 plus x squared over 2 factorial. So basically, if you take the first two terms, then you can say like ln of 1 plus x is x, if x is small. So you can say like, well, this term is kind of like x minus 1 or something, right? So, and then you have kt, right? So you could say like del c would be like del x, but you have a kt here, so dkt, which that's the definition of this m. What m is, the Stokes-Einstein equation is that the diffusion coefficient is kt over 6 pi viscosity times the friction factor, viscosity times the radius of the, say if you have a particle, the diffusion coefficient of a particle is kt over 6 pi viscosity times the radius of the medium, you know. And then this thing's called a friction factor. And then the friction factor, it turns out, is 1 over this mobility. Capital M is not usually a symbol that's used for mobility. Usually a symbol for mobility is mu, but unfortunately mu is used for chemical potential in this argument. So you have to call it M here. But anyway, so you might see at some point people talk about the friction factor. That would be like velocity times the friction factor is the force. Like if you have a particle and you drag it, this is like the kind of a drag coefficient for a subatomic particle, say. You know, so and you can calculate with Stokes' law, 6 pi times the viscosity times the radius. So this is called the Stokes-Einstein equation. This diffusion coefficient of that thing. So he's got, so if you do diffusion coefficient or divided by KT, you get this mobility. 1 over this friction factor is the mobility. So he has this equation for Fick's law, they call it the generalized Fick's law. This seems pretty general to me, the first one, and understandable. This is a little bit less understandable, but it kind of makes sense that here our concentration fluctuations going uphill, it's going against the concentration gradient. You would say it would not decompose, right? And the only way that it could possibly decompose is if the thermodynamics forces it to decompose, then you have to institute a thermodynamic driving force for transport. And the place to stuff it in is in Fick's law, and then you can go ahead and on your merry way, accepting that this is the way the world works. You know, so that's kind of a jump, you know, in a sense, but basically that's how you get this. You need that first step to get the whole thing. That doesn't even solve the problem though, because you'll end up with. So the equation you want to get is this thing like dc dt, so it's like this same kind of Fick's law looking equation is this mobility times and then d squared f dc squared, which is kind of del squared mu. That's kind of that term. And then it's got this weird series of concentration dels, del c squared minus 2 kappa del 4c. So this takes care of all the problems with spinodal, like the rate of phase separation depends on the thermodynamics. So F is the Flory-Huggins, or it's the Hildebrand equation, right? And then I've been watching a TV series where one of the characters is called Hildegard, you know, and it's like thinking, is it Hildegard or Hildebrand? But anyway, so I don't recommend watching TV though. It's like I'm addicted to it. So anyway, d squared f dc squared, and then delta, maybe it takes care of the units or something. I don't know. But basically, this equation comes out of nowhere as far as I can see. And you can read if you want to see where it comes from, you know, you can kind of look. this guy derives it. This wherever this is lecture 24, this is a derived in this thing. He derives that equation. You can see how many pages it takes. It's like, and you lose track really fast about what is going on here. So anyway, and I think this is a simplified version of deriving it. So if you want, most people that use the spinel don't know how to derive that equation. That's my feeling, because I don't see anybody talking about the derivation of it, like any place. So anyway, that's where things stand. So once you have that, equation, then it's pretty easy to get the once you have this equation, then it's just plug and play to get the maximum Q's, like the derivative. Just take the derivative of so this is that equation, the second order and the fourth order, and then you have this is your Flory-Huggins equation or your Hildebrand equation. That's the mobility you can get from the diffusion coefficient divided by KT, and then this gives you the rate of growth of the phases. Oh yeah, you plug and play a let's see, he does that in here somewhere, but you plug in an equation. You plug in this equation so you use that as your parent equation, and then you use this as your parent equation. You plug in a concentration fluctuation like what we had, sine Q dot R with an A in front, but you include a time term, right? And this omega is the rate of phase separation. So the rate times the time gives you that. So you want that rate of phase separation. You want to find where that's maximum. So you want to find where that's maximum, you plug that into this equation. You take the derivative and you find out where the rate is equal to 0, and then you find the Q max for that. It's just like a standard differential thing. So then you can find the peak value. So you have the peak value, you have the 0 where the growth would be 0. So if you plotted, so typically what people are going to do, and if you look in that Hashimoto, what he does is people will plot like so you can measure the growth rate. I mean, if you do light scattering, shoot a beam of light, it's kind of microns in size, like 0.6 something for red laser. Shoot it through a sample, and if the phase separation is happening on a micron scale, then what you'll see if you put a piece of paper here is the main beam, and then there'll be like a cloud here, right? So and that's Q max, like the distance from there to there. So 4 pi over lambda sine theta is going to give you Q. So the angle here is theta, is like you can calculate from that. And then 4 pi over the wavelength of the light, this 0.6, gives you the Q vector. And the vector is isometric, so it doesn't have a direction really. And then we're at that position is Q max. Q max for this growth. And then you can plot the intensity at Q equals Q max versus time. And that's going to be like this growth rate, because the growth rate equation is going to be exponential RT, then you want to take like, do like log of the intensity, it would be a straight line, and it'll go to a point. So you can get the slope of that to get the growth rate, basically, will be the argument of that exponential. So the slope of that will be the growth rate, and you can plot growth rate as a function of like Q. When you do that, it'll have a peak in it. The peak will be at the same position as what you see there, and then it'll go to 0 at some point. And that's your Q critical from the first part. So you can get the Q max and the Q critical by doing this kind of simple experiment, like a light. You just shoot a beam of light through the sample, you get a ring, measure it, and watch it grow. That makes it kind of nice. And then this theory, despite how complicated it is, can predict every feature of that curve. And from the features of that curve, you can predict the features of the actual curve of the scattering pattern. So you can predict everything that's happening with this kind of thing with these two equations, basically. It's just a nice tight package. Like it's demonstratable that it works. The derivation of it is a little bit pretty dicey. It's hard to do. The first part, the Q max part, this Q critical part, that's not that bad. I mean, that's the first paragraph of that wiki page, which I think he gives. I mean, you can figure that out. This part where you get Q max is dicey because you have to figure out what does chemical potential have to do with composition, and how do you plug that into Fick's law to talk about reverse diffusion that's driven by thermodynamics instead of by concentration gradient? So it's complicated. Anyway, you're not going to die if you don't figure this out again. Like, but basically, it's something that's there. You normally, like, no one that's going to ask you a question is going to know how to answer it about spinodal, because it's like too much. I mean, they had all right, at the American Physical Society meeting like 5 years ago or something, they had like an anniversary of Cahn-Hilliard theory, and they had like a whole week of just people giving talks about Cahn-Hilliard theory. And there wasn't like one talk where they said like exactly how you derive it, but everyone's using it for different things, so, and there's a lot, you can tell, like, it's going to attract attention. So that's why that paper's in Nature, basically, because it's like, it's going to be a topic that everyone kind of learned, and like, so they kind of, anyway, so basically it ends up being that, yeah, sorry, yeah. So anyway, yeah, so this is that Hashimoto thing. So there's a bunch of papers in there on the web page about spinodal. There's just a huge bunch of things here. So let's see. Let's see if I can find the homework here. Let's get to that. That's not what I want. How about new? That's good. I already had this open, but now I feel like I'm picking up a cold or something. Well, that's our Korean guy. Oh, it's Korean. Nice. Okay. Thursday, you can't be here. It's something. Okay, so this just goes through like how you can use spinodal, and what these guys are doing is this. So they're doing something seemingly neat, but basically, again, they aren't doing anything. They're just doing like computer simulations. Not even, they're doing, right, they aren't even doing computer simulations. They're doing machine learning, okay, which is kind of like fake computer simulations. And then, so the graphics, so they have a really nice graphics team. So like somehow they can make it that they're making these tooth implants, and the gradient, spinodal gradient structure that's going to match up with the bone that you implant the tooth thing in. And then you can also make, everyone, all old people are interested in teeth, they're falling out, and like, and then if they're not interested in teeth, they're interested in hip implants. Like every old person is either like knee or hip. Not me, but everyone else. So like they can hit every spot here. It's like bingo. So anyone over like 50 years old is going to be like, yes, this is my paper. I know all about acetabular cups and like, so they hit a sweet spot with that. So basically they want to make this structure, and they want to be able to test it mechanically before they go ahead and make it. I mean, making it is really the problem, right? So, but they're going to make money off simulating it and saying that they can do the mechanical tests on it, and then they'll be true. And you can also do the diffusion tests through the structure and all this business. So you can do all the tests that you would want to do on a computer, and you can kind of design the structure so it would be a good whatever, either tooth or hip or whatever, right? So that's the idea, that they can, that there's a niche where you could say, like, you could make these things. So they're using machine learning. So they aren't actually doing a simulation. So what they do is first they run a simulation, right? So the simulation is based on this thing called what's it called? Phase field simulation, which is, if you look at it, phase field simulation is almost the same thing as what I said. Like, there's a concentration gradient that adds into the free energy. Sounds just like Cahn-Hilliard, and then you have the free energy and this concentration gradient term. It sounds like phase field simulation was built for Cahn-Hilliard. So he has this is I think this is loosely our diffusion equation that we had, where this is kind of the chemical potential gradient, except it would be the second derivative. So he's got this dot derivative, which is that thing is if you have a vector, if you have a vector in the argument, it's the same thing as the del squared derivative, except that the argument isn't concentration, the argument it isn't a scalar, the argument is a vector, and it converts the vector into a scalar. You still end up with the second derivative of the thing dx, like the d or d dr, d squared dr. It's the same thing, except the argument is a vector instead of a scalar, this dot thing. So it's still like, this is still like del squared. This is still like the quote unquote generalized fixed law, it's fixed second law, to talk about concentration changes in position. So this is basically the beginning of the way to get a maximum size in the fixed law, but it isn't using the free energy expression, right? But they're kind of linked together. In other words, they both have this kind of kappa thing and all. So instead of that, so the kappa term in the Cahn-Hilliard thing is basically, kappa is basically going to be this term, like this concentration squared minus 1. This is called an entropic free energy related to an interface. This kind of phi squared minus 1 phi is entropic free energy. In other words, in order to position things into, I think what it means is like, in order to take things and put them into an interface, they can't be free to move around anymore. So they're stuck there. So the entropy is decreased. Right. So this term is kind of taking care of the entropic part. And then I guess this is the bulk. Let's see. First term is a gradient energy concerned with phase interface. And the second term describes the chemical free energy. So that sounds backwards, but basically this has something to do with the free energy expression we had before. So the first question is like, figure that out. I haven't exactly figured it out, but basically there's some connection between that and the Cahn-Hilliard. He says that it's obvious, it's kind of obviously linked. But all right, so that's part of this. Wang calculates with equations 3 and 4. So it's just like try to figure that out as best you can. I mean, I won't take many points off on that. It's just like try to see how you can fit the two together. Try not to lie about it, but if you can't, as a last resort, but explain how these equations are related. So just try to piece that thing together. And I cite this thing, but I think maybe the wiki page might be better to look at. You can look at this too. There's a bunch of things, but basically maybe the wiki might be easier. The nice thing about this is it's an experiment. Like usually you get a theoretician talking about this stuff. And here we're using a simulation guy and it's worse, But so this is actually an experimental group using and trying to describe what Cahn-Hilliard is. That makes it a little bit more down to earth for me. But anyway, so then he's using these things like some words. So what he does is he simulates. So he's going to simulate. So you see these little squares. So he's going to simulate these little squares. Okay, so he can't simulate a whole hip implant, right? What he can simulate is a square, a 64 grid, 64 by 64 by 64, and each of the little things is called a voxel. Maybe you've heard of that before. So it's like a pixel, but it's this volume. Right? So it's a voxel. So 64 by 64 by 64 voxels, whatever that comes out to. And that's as big as he can get with this phase gradient simulation, whatever he's using. And he can make 6,000 of those. So he can decompose and make these structures, right? And he can make 6,000 of them. He's going to use, I think he uses like 4,000 as what he calls a training set. Right. So with this machine learning, you have a training set and then you have a test set. So the other 2,000 is going to use to test whether those things work. He's going to compare like what he gets out with. So this is like the 2,000 to compare these same moduli that we had from we had last week, right? This was it last week? Didn't I go through this modulus thing? C11. So C1 is C1111, like sigma 11, eta 11, stress and strain. Okay, so these are the same C1, 2, 2, 3, 3. So it gets up to 6. Those go up to 6. Those are defined up to 6 because you can match the 2 and the 2, and each one of the things has 3. So it's actually think 64 total, and then there's a 16 independent because some of them are 0 and it's symmetric. So 64 goes to 32 because it's symmetric matrix. And then notice the top and the bottom are the same number, like 1, 2 is the same as 2, 1. And then the sum of them are 0 because you can't have a change in something with something. I don't know, it works out that way. So anyway, those are the C things. So he's showing that the mechanical properties of this thing that he gets. I didn't ask you how he got those numbers. Basically, he gets them somehow by Fourier transforming the 3D thing, and he gets a modulus in the different directions from it. I believe he could do that, but I mean, he explains that in the appendix. He explains that to some bit of detail, which you might be interested in looking at, but it's not really the main point, I guess. Maybe it's some part of the point, but anyway, so in that phase field, he can simulate these things as a function of time. Right, so he's 6,000 of them, and then each one of them has a time sequence up to 100 time steps, whatever a time step is. So he does some kind of change in he just lets it evolve. He starts with a random concentration thing, then it plugs in those kind of Cahn-Hilliard equations with the gradient, and then it decides where it goes. And he takes that as the next starting point. So each time he takes a starting point and calculates, that's a time step. So he does that over and over and over again. And this thing decomposes and looks just like Cahn-Hilliard. Looks pretty good. Right. So at first you'd say, so looking like it, since it's something that has a periodicity and you look at it and you can't see it, then looking at it is totally useless. That's one thing to say about this paper. Like graphics of spinodal are useless because you can't tell, like our eyes can't see the periodicity in it. So you could only see it with something like a laser, something like do a diffraction pattern. So anyway, so it's a little bit misleading to show, oh, the pictures look good and they look like spinodal. That isn't a real good judgment of this thing. You know, it's like saying you can see something invisible. That's why it's perfect. You know, so anyway, but it does have behavior that behaves like this. So he calculates again the correlation function, which is this 2-point or binary or whatever you want to call it. What's the other words for it? You guys had some other things for correlation, but anyway, he calculates a correlation function for the structure, and it has a peak in it, kind of, not a huge peak, but a peak. That's good. That means if you Fourier transform a peak, it turns into a peak. So the diffraction pattern is going to have a peak also. So that's good. There's another little twist about about correlation functions. That there's a linear part at the beginning where it's like a number plus the surface to volume ratio times the size. So the slope here is the surface to volume ratio, which means the steeper slope has smaller sizes because smaller things have a higher surface to volume ratio. So the steep one is small and the other ones are larger, right? And these are at different volume fractions, and like the squares are 45%. So it's good. The low volume fraction has small sizes. That kind of makes sense. That's good. That's a good thing. And also the peak is at a shorter distance for the lower volume fraction too. So everything's smaller when you have a lower volume fraction. It's all consistent. That makes sense. He doesn't mention that in here, but this kind of shows some consistency. Then I think the 2 or 3 that he does, they're for different size matrices to show that he doesn't have a size dependence to this thing. Because what he does, so he's going to take so in computer simulations, what you do is this. You go, right, so normally, if you have this and you want to say it's going to go to infinity, so I have like this position, so you'd repeat that position over here. So it's like a mirror, right? Then you repeat it here and here. So this thing would repeat like that. And this thing is a 64 voxel box, right? And he's going to infinity. He's going to macroscopic. He's making a hip implant. So this is infinity, essentially, he's going to get to. So, because the spinol is going to be a micron. It's going to be kind of a micron. This is going to go to like kind of centimeters. And so it's a lot more. Anyway, so that's in 1D, and then in 2D, so you have to figure out how you're going to do this kind of repeat in order to put the thing together. And that's what he calls this. He calls this so, and then his simulation also, he has to have, so the concentration fluctuations here are gonna rely on what's next to it here. Right, in other words, it has to draw out, somebody's just drawing out from here to go to there. So in terms of a dynamic system, this becomes kind of interesting how that's gonna unfold. So at the initial stages, he has to have a thing called padding, which means he's going to either initially have this thing be 0 or have that thing be some number or have this somehow mimic the random thing he had over here. Right, so it's kind of several choices you can have in terms of padding the sides of this thing during the initial simulation, that phase, whatever he calls it, phase gradient or something simulation, the phase field simulation. Yeah. So anyway, so that's what the padding thing is. Yes. Oh, switchback. All right. Sorry, I didn't hit project. I hit the PC here and not the project thing. So, all right. So that's kind of, all right. So anyway, you can kind of read about how this works. He shows a little bit. So you have the training sets, and then you say like, what you have to do is break down the structure into numbers. And then, so you're going to have a series of features of the system, like concentration versus position would be one. And then like density of the whole system. And then like you could do a Fourier transform of it and get that peak position. So, and then you could get the transport through it if you wanted, or you could get the C1, C2, C3, all the mechanical properties, C11, C1, whatever. You get all the mechanicals of it. So you get all those numbers. And then you can say, you can write a linear equation of the first number plus the second number. You put like a weighting factor because they're different things. Like one is a modulus, the other one's going to be concentration, and the other one's going to be like periodicity, size, position, right? So you have like different things. They have to have different weighting factors. So how do you decide if you're going to sum and say like it's a good match? In other words, I duplicated the thing that I had. You have to have some kind of algorithm where you say like how you weight those different things. So you have to write an equation. So it all has to end up being like yes or no in the end. It worked or it didn't work. So somehow he's going to figure out a way to write a linear equation to sum together all these things with these weighting factors. So there's a thing called like a weighting matrix. It's going to weight the parameters, and you can kind of see, you can evolve that weighting matrix through a routine, so you can change it and see if it worked, depending on how your final outcome comes. So you're gonna do your simulation. You have all the things stacked up, time sequence, 6,000 of these, right? And then you're gonna take 4,000 of them, and you're gonna say like, what is my weighting matrix gonna be? And then with that weighting matrix, I can recreate the structure. Like I can, with that weighted parameter set, I can go back and loop and recreate the structure. And then I can go and compare the two structures and see how well they agree, right? So basically it's kind of an iterative training thing where you keep feeding things in and seeing if the answer comes out right, and you change those weighting things. So a lot of it comes down to writing an equation that could describe the thing, a linear equation, a sum of terms, and then the weighting factors are adjusted as you loop through this thing in a nutshell. And that's kind of how this is going to work. So anyway, so he claims that like, yeah, you can get a perfect match. Like you can get, so there's a training set and then he tests it on actual samples. Like I'm just going to put in the same input and I'm going to see if it matches up with the sample that I produced with that phase gradient, whatever simulation. And they match okay, I guess. I mean, it's kind of hard to tell what would be a good match and a bad match, but the blue dots seem to be on a straight line on the match line. So, and then so basically that's how he tests to show that his simulation is working. In the end, like he's doing this because once he gets this thing trained, he can spit out these things in 2 seconds, and the phase simulation takes a day. So the 6,000 took him like a year or two to do. Then like he can spit this out in like a couple hours. He can do the same thing, and he claims it's the same thing. Like it's exactly the same. And because of that, with the phase thing, you could never make centimeter size objects, but because he can do it in such a short time with his kind of fake cheating thing, then he can make the whole implant, and also he can change. I didn't see exactly how he did the gradients and all, but he can do gradients with his simulation, with his artificial intelligence thing. So then he can tune it to get anything he wants. I guess at first I thought this was pretty stupid, but after talking about it, I convinced myself that it's not that stupid. It's kind of could have a use, you know. Maybe at least in making movie graphics or something, you know, like Space Wars or whatever. But so who knows? Anyway, it's kind of take a look at it if you haven't seen this stuff before, just to get a little bit introduced to like the simulation thing and also the spinodal. I mean, it's using spinodal, but it's in this frame of this artificial intelligence stuff, like how. I mean, GPT is doing the same thing, but with like with text, you know, and copying text from the web, and then kind of going through a routine. It has a big test space where it can learn, and then it tests to see if it actually reproduces. It's the same routine, it's just with words. So there's that business. I guess that's okay. Let's look at the questions here. So uses circular padding to deal with There's a paper in here on circular padding. There's a paper on padding somewhere in here. Capacity. The CIJ, that's it. C1, 2, and 3, the padding thing, circular padding. This thing, it's a paper on a different subject, but it's kind of talks pretty well about what circular padding is. I mean, he shows a graphic in here that shows it. In other words, he's talking about the edges of a simulation and how do you, he's simulating a rough surface here, so it's kind of a 1D problem, which makes it easier to figure out what he's talking about. In other words, he has to fill in the red part, he has the blue part. So how's he going to fill that in? In other words, padding means you're filling something in. So this is he's showing what circular padding is like in 1D. You know, it's not a voxel thing, but anyway, he shows kind of how that works. So you can see like this blue thing is the same as that blue thing. There's original data, and you can patch it in kind of from the different parts. So somehow that's circular. Like taking from here, putting there, that here, and the thing all works out. It's because you have to take the 64 voxel and then you want to go to like infinity, and especially in the initial stages of the thing, you know. So anyway, so that's that business. All right, so there's a certain signature. So they talk about constant mean curvature. Hashimoto also has a paper where he determines constant mean curvatures. It's linked in there somewhere. Stochastic, so it's random, but has periodicity and interfacial concentration gradients that go against Fick's law, reverse diffusion. So figure 4b is basically those correlation functions. So this is just what I said, like the surface to volume ratio. So 1 over that is the size, so that matches up pretty well with the concentration. And then the peak position also matches up with the concentration. In other words, it's in real space size. So basically it's just the size gets smaller at the lower concentration. And then, all right, so then there's this problem that is the problem that he seems to skirt around. So he's got a fixed 64 voxel thing, right? And then he shows the correlation, and he's got a thing that's centimeters large. So he's got thousands of voxels in his simulation, his machine learning thing. So he has the ability to write a correlation function to thousands of voxels, but he only writes a correlation function to like, I think 100 or something. Like he goes beyond 64. No, he only goes to 30. He doesn't even go to 64. So what would happen? So say you just had tiles, you know, like a floor tiles, and they repeat a pattern, so it goes out. It can go infinitely, right? But if you put that into like a Fourier transform, like you'd see a big spike where you get to the next, because each tile would be in a cubic crystal form. It would have a big spike. Right, so this correlation function, like because he's got this up to thousands of voxels when he makes his final simulation, but he only shows up to 30. Right, 30 is interesting for spinodal because that's the peak in this line part. And then it goes to the average concentration here. So you could also get that. There's a correlation function. I should ask that too. Like the square is the low concentration, should be 45. So when this goes to infinity, these numbers at this end should go to the concentration, which it doesn't. That's kind of weird. It should be 45, 50, 55, and he's got 55, 50, 42 or something. Oh, wait, that's 45, that's 50. I guess, is this, anyway, it doesn't look right, but basically the middle one's all right. This one, 55, should be, oh, the triangle should go to 55, I think. Should go to the concentration out here. Anyway, if you drive this out to 64, if he successfully did this circular padding thing, there should be no peak there. If he didn't, there should be a spike. There should be a big spike. And that big spike means he hasn't created anything like what real spinodal is, especially macroscopically. He's talking about like cells can grow in over microns or huge distances, centimeters. And it's going to, so basically if you have walls set up in tiles, that's going to significantly interfere with the process. And also he's talking about the transport. He can calculate what the transport is through this. And if it's really 64 voxels, because if you have a spike in the correlation function, that's going to dominate the transport. In other words, it's going to go its merry way through the 64 voxel, and it's going to reach that place where it doesn't match up. Then like the game's over for transport. It's got a problem because they aren't lined up right. So anyway, so this misses out on that feature, like this should keep going and go at least to 100. So you could see. Anyway, so that's another thing. So what appears, figure 3a shows Oswald ripening. So Oswald ripening, I didn't talk about that. So anyway, basically the phases will, let's see, PowerPoint, Oswald ripening. So Oswald ripening just means that the big phases eat up the little phases. Things grow like over time if you let them mature. So it's basically for one thing, the small phases have a lot of surface area, and then the big phases just can have a lower surface area. The surface area is a penalty, like there's an energy with the surface, and they want to just consume each other. So it wants to grow. But the original Oswald was about when you nucleate metal crystals, and you have different polymorphs for the crystals. Right, so you have different possibilities for what kind of crystal you can form. Let's see, it's in here somewhere. You have polymorphs. So you have like titania usually is anatase or rutile. One of them is like catalytic, and the other one's sunscreen. Right, so if you put the catalytic one on for sunscreen, you get skin cancer. So it's not a good. You want to know what crystal form you have for titania. Silica has a huge number of crystals. Right, so those are all polymorphs. So each one of these, say at a given temperature, they'll have different free energies, and one is stable at the temperature where you are. Right, so there's a stable polymorph and a non-stable polymorph. It's like diamond is stable, graphite isn't, but there's like a kinetic problem again from graphite to. Anyway, so Oswald originally was talking about polymorphs, and it turns out when you crystallize from a melt, the least stable polymorph forms first. So you get a lot of little least stable polymorphs, and then they're consumed by the more stable polymorph. And that's because the least stable one is kind of closer to the liquid and free energy, so it's got lower surface energy. So if the smallest possible crystal, then the smallest one would be the least stable one, because the surface energy is dominating the energy, and it wants to make the worst one. So it's kind of a contradiction. Basically, the big ones that are more stable eat up the little ones that are less stable because they're different polymorphs. That's the original Oswald ripening. That's been taken to mean like things grow in size like this, but like this is spinodal from polymers. In the early stage, you have like a fixed size, that's the Q max, intensity versus Q. When as time goes on, so 1 over Q is size, they get larger. goes to the left. So the peak shifts to the left. That's termed Ostwald ripening in spinodal. It's like a late stage spinodal. And in the end, the peak just disappears and they just become dots as if they were nucleation and growth. So in the end, you can't distinguish between the things. So that's what that question is about. Ostwald ripening, explain how does figure 3A demonstrate it? 3A shows Ostwald ripening, I think. Yeah, so this is basically Ostwald ripening for spinol. He starts with small phases, then as it matures, they consume, the small ones are consumed and the big ones grow. Then the big ones get larger and larger. In the end, they're just gonna like clip off and just become dots, like spheres, just domains, right? So in the end, they just become domains. So as it matures, and it shows that, like he's got that feature going on here. So that seems to be pretty good. That kind of indicates that it seems to be working out pretty well. Then he's also got that because spinodal is governed by these thermodynamics and diffusion, and it's kind of fixed numbers, so it's kind of a quantized size. So he shows that he has a narrow size distribution for the struts in here. Everything works pretty well, and he kind of knows what he's doing. I mean, in terms of showing that it works. And then this is his transport thing. He's got the transport measurements done on the computer. So actually, they did quite a bit here. So let's see. So that's that business. What is the final result? The final result is going to be that you can't tell nucleation and growth from spinodal. It'll just look the same. You get just domains like spheres. 3F and G demonstrate some of the expected behaviors of spinodal. We'll go through these two figures, F and G. What features are being demonstrated? So 3F and G. 3F, stochasticity, and G. So he's shown that it has a narrow size distribution in F. This is just showing, I think this is showing the different CNN, that's his thing. PFM is the original learning thing. And this is one that didn't work, I think. So he's saying, like, you can tell the difference between these. So this has a broader pore, these are narrower. This is his kind of experimental, even though it comes from a simulation, and this is his machine learning. And he's saying they're indistinguishable. Yes, that's what the argument is here. And he shows the picture so you can see. Again, you can't see what's going on from a picture. So, and then F and G, this is showing how the transport works through these. So I think he's just showing, did I really say G here? I think I said F and G. So G is the transport. It's just showing that the transport. So I think he's trying to show constant diffusion model result, concentration distribution for 3 porous structures. It's just showing the transport through the structure. This one, I mean, these two are the same and that one's different. I guess that's one thing. And I guess the spinodal structure should be uniform. I think that, I didn't mention that, but it should be like a uniform structure. So this one isn't uniform. I think that's kind of what's going on with this. It's like a uniform structure, non-uniform. This is conventional, means some other computer simulation method. I don't remember what it is, but this is our phase field, whatever. And this is blobs. I don't know what blobs are. I don't remember. But anyway, I think it's just shown uniformity in G. You might have a different answer, but and 5 and 6 are the mechanicals. So explain CIJ values, how they relate to mechanicals. Just figure out what that is, because I think this is the second time we've seen that CIJ thing. So it's in this. There's a link. There's a book, Mechanical Constitutive Equations, Model 3 with Solutions, and there's 2 books in here. There's this old book. He references this old book, this Dynamic Theory of Crystal Lattices. And this is actually a pretty good book. Like I hadn't looked at it before, but so let's see. But it's not, I don't think it's good for what he's I don't think it's good for what he's using it for. But it's pretty good for heat capacity and stuff. It's actually a pretty good book. Like I kind of started looking at it. Wherever that is, it's down here. Heat capacity and mechanics. So Born is the guy, the Born whatever theory, right? And in the book's an old book. You can see it's from like some, I don't know, 60s maybe. Max Born. I didn't know he was at Edinburgh, but anyway, this book's pretty good. See, where's the thing we can zip through this thing? Let's see. Yeah, he does go through the C123. Anyway, we can use this book later on somewhat. It's got a pretty good description of like the heat capacity stuff and pretty good book. But he does do that C123 thing, but it's not particularly readable. The better thing is the that other thing about CIJ continuum mechanics. This is just like something that just says exactly what it is and lists all the values. Like so it's a symmetric matrix, bottom ones go away, and then a bunch of the values is zero. Like here. So you end up with like 13 of them, I guess. And there's they rename them. I'm not sure how they name these things, except just to remember them. But like so they're numbered up to 6. There's probably some way to get the 6, like 3 + 3 is 6 type thing. I don't remember. Anyway, so it's just kind of like what are those? That's what E is. Let's see. Let's see what else. So there's something else in here, I think. Polymorphs. Yeah, Oswald is like he was in the 1800s and he had 500 papers and 45 books. It's like that's amazing, you know. Like in the 1800s, people would usually have 3 papers. Really, like famous people would have not that many papers. I don't know how many Einstein had, but it was definitely not 500. It's more like 15 or something, you know. So it's kind of weird. This is just something that shows. It's a paper. The paper is on the web page, but it shows Oswald ripening. Like you can see the different stages, and there's like nucleation of the unstable phase and then growth of the stable phase by consuming the unstable phase. That's kind of what this whole paper is about. It's about Oswald ripening. So you can see like the small go to big. And they do analysis of what the crystal structures are. Same thing here. It's just like this is X-ray diffraction. So instead of having a diffraction pattern like this, they take each peak, so they do a color coding of the intensity, and then you can do it as a function of time. You can see where the phases appear. So they start out with amorphous, and then the different crystal phases show up. And it's basically Oswald ripening. Like you see, the more stable phase shows up later and consumes the less stable phase. Here it's like the stable is cubic. It starts out with a lot of hexagonal, and then the cubic consumes the hexagonal, and the hexagonal goes away. That's kind of the idea. It's like just classic Oswald ripening. But these are both like this. These are both 2020s. These like recent papers people doing, just kind of showing Oswald ripening. But you know, those things, yeah. So that's just some Oswald ripening stuff. What else we got? That's about it, I think, for this stuff. I kind of went through this stuff quickly, but hopefully that's okay. I mean, it's just to give you a feel. You don't need to be an expert in spinel decomposition, definitely. But if you see the word, then you'll know why people are in other words, why does it end up being a nature paper? It's like, because a lot of people put a lot of time into developing the math for it, and it was kind of a unknown thing. Like, in other words, you're in this region, you get this kind of web-shaped structure, and then, oh yeah, that's interesting. It's kind of like pretty, but what do you know, where did that come from? And then so people thought about it, and the final solution, I guess, is like Cahn-Hilliard theory. It's pretty involved, but because it was involved, it kind of attracted more people that are interested in involved things like that. And then like it kind of grew out of that. And then because the framework, we can predict all the features of the growth, then it becomes kind of interesting to see when it works, especially when it's so complicated that you can't really understand it. When it actually works, and it's surprising. You know? So I think that's more or less the gist of it. But I don't know. That's about all I have today, I guess, beyond this thing. But I think next week is like do surfaces, so look at like surface, then nanoparticles that go with surfaces. So kind of coupled together. Mm. Some of the people, like for last week's homework, some people were gonna like redo it. So if anybody, I don't know if you guys want to do that, but I don't really encourage it, but because people got 55 and they asked, can I redo this thing? I mean, I'll look at it again. Doesn't matter, but basically, probably won't make much difference, but if you want to, I think two groups are doing that. So